So next I'm going to show you probably one of the most important applications of what you guys have been working on with parallel plates and electric fields and that type of stuff. This is an apparatus from over 100 years ago, from like 1909, 1910, and it was made by a guy named Millikan. And you can sort of see a few things on here. Millikan did his work, a lot of work in Chicago, so great for hot dogs and deep dish pizza and that kind of stuff. But it's almost looks like a pressure cooker, but it's not a pressure cooker. But there's a few things on here. For example, this is like for it looks like there's like a little viewing thing, like a microscope type thing. There's some controls on there. There's some wires and stuff. There's electrical stuff involved. It does involve pressure. You can just tell by the general structure, really solid structure. And right here, this is called an atomizer, which basically like almost like a little spray bottle type thing, like they used to use for perfume bottles and stuff like that. And there's a nice little like a ruler down here. It's in inches and stuff. That sort of gives you an idea about how wide this was. So that's around 18 inches. So this is about like a foot and a half or so. That's about how wide the entire apparatus might have been. So anyway, so this was used by Millikan in around 1909, 1910 to do some really important work that we're going to get to in just a second. Now, let me show you a different picture to sort of show you how things work. So this is more of a cross-sectional type, cartoonish type version of what his apparatus is sort of like. At the top here, in this top chamber right here, that's sort of like the little spray thing that I showed you before, would spray in this mist of oil droplets. And then these oil droplets, what they would do is there's a metal plate here and there's a hole, and these droplets would actually fall down through that hole and then fall down over here. And here's a positive plate and here's a negative plate. And when these things would go in there, just the spraying of them, static electricity can charge them, but you can also charge them by using X-rays. When you hit the little things with X-rays, you can charge them negatively charged. And when these things drop down and are charged, you can then use the positive and negative metal plates to make an electric field to actually control the motion of the charges as they go up and down. So as these droplets are dropping down the actual apparatus between the plates, you can turn on electric field to try and control their motion. Okay, so let me sort of show you what that might look like. So here we have a Millikan apparatus, a little animation I can show you. And what's going to happen is you got on the top right, you got sort of like the little spray bottle type thing that sprays in that mist. And then the little tiny droplets can then go down through the opening and then they start falling down. And this sort of represents the X-rays going across, charging the droplets. So they can be electrically charged and controlled by the plates. So now if we actually took a good view of them from the side there, using the microscope basically, or telescope, whatever you want to call it, so you can actually see the droplets. And when the voltage is turned off, there's no power, the droplets just fall down, and you can see some of them have little charges on them. But when the voltage turns on, you can see that some of the droplets stop. So certain droplets keep on going, but like this guy right here, he kept on going because he had no charge. These two guys both have a negative on them, and they've actually been stopped. These two guys right here actually have a lot more negative. They got like 2 negatives on them, and they are actually going to start going up. So depending on how much charge is on them, different things would happen. So obviously if the negative charges are being stopped and slowed down, let's reverse this a little bit here. You had to have the positive plate on top, and the positive plate was on top in order to attract the negative charges that were inside the apparatus. And then as it kept on going, the ones with more negative charge would actually be attracted up. And that was the basic idea, is to control the charges. Okay. Let's look a little bit at how the sort of all pieced together and what we can get out of this. Okay, so here's just a little screenshot or clip of the apparatus from the video that I showed you before. And we've got the droplets, got the positive plate on the top, got the negative plate on the bottom. I'm just gonna draw those out a little bit here. That's not even close to being right. Let's get rid of that. All right, that's what I want right there. Okay, so you got 2 plates, one on the top, one on the bottom, something like this. Okay, so positive plate on the top, negative plate on the bottom, which means the electric field in this case would actually be going down between them, from positive to negative. And inside of here, there is a charge, and those little charges, of course, were negatively charged. I showed that in the video. Now, the whole idea was to get them to stop, use the electric field to actually stop the charges. Because if you can actually get it to stop, you know the forces are all equal. And there's two main forces acting on this thing. Obviously, we have the force of gravity going down, and we'd also have the electrical force going up. So this is what Millikan wanted to do. So what Millikan wanted to do, and this is like called a Millikan apparatus or the Millikan experiment, he wanted to have the little charges, the little tiny charges that are going down, the little charge droplets. Basically, he wanted to have those little tiny charges in static equilibrium. Okay, we've talked about static equilibrium before, where all the forces are equal to each other. So basically, you've got Fe is going to be equal to Fg, or if you want, QE, we can even use the same type of Q, it doesn't make any difference. We can use QE is going to be equal to Mg. And the reason why he did this is because he wanted to analyze the Q value. He knew what the mass of the droplets were because he knew how big they were. He could use the density and actually their terminal velocity as well to figure out how heavy they were. He knew what the acceleration due to gravity was. The electric field he knew because he's the guy who set up the plates, no big deal. Q was the only thing he didn't have. And one of the things he wanted to know is what possible Q values can you actually have? Can Q values be anything you want? And that was one of the big questions that he had, is can Q values be anything? And he wanted to know if they could be any value that you want, or if they were actually quantized or made up of certain chunks. So he did this experiment, cajillions of times, and he found Q value after Q value after Q value after Q value. And he found that the Q values were not random and they weren't continuous, that the Q values were actually quantized. They weren't any random value that you want. What he found was they were always a multiple. These Q values were always, always, always a multiple of the 1.6 times 10 to the negative 19 coulombs. And he's the guy who actually found that value. He always found that the charge was actually a multiple of 1.6 times 10 to the negative 19 coulombs. That was the common factor with every single Q value that he actually found. So because of this is how we found the charge of the electron, of course, eventually the charge of the proton. And this was actually then used and put back into the Thomson experiment of the late 1800s to then find the mass of the electron, because Thomson has found the charge to mass ratio, but he hadn't actually found the charge or the mass. And this was actually then taken back and put in that ratio to actually solve for the mass of the electron. But this is why we've been using that value so much in our calculations, because the charge of the electron is a multiple of this, is that number. Charge of proton is that number. And any nuclei is always a multiple of that number. So for example, having a charge of 2.0 times 10 to the negative 19 coulombs, that charge cannot exist because it's not a multiple of this value. It's got to be 1.6, or it could be 3.2 to the negative 19, because that is be two protons put together like in helium. But you can't have like 4 times 10 to the negative 19 coulombs. That is impossible. So whenever you have a charge value, if you divide that charge value by this, it has to give you an integer. If it doesn't give you an integer, that charge does not exist. And this came out of the Millikan experiment well over 100 years ago, like 110, 111 years ago. So it was a really, really, really important application using basic fields, using the basic static equilibrium idea, and balancing out forces. Okay, so let's see if we can practice with that just a little tiny bit here. Okay, so here we have a proton between two plates, and the proton is perfectly balanced. It's in static equilibrium. So what would the electric field be? Well, I've got two forces acting on this proton. I've got the force of gravity, of course, is going down, and I've got an electrical force going up. And if this thing is balanced, I know those two forces are going to be equal to each other. So QE has to be equal to mg in this case. So I have the mass of a proton, I have the charge of a proton, I don't know what the G value is, I got all those. So I can just go ahead and solve for my electric field. So that would just be the mg divided by the q. So if I multiply out my mass and my gravity, I got the 1.67 over 27. I can multiply that by the 9.81 to get the force of gravity acting on my proton. And then I would just divide that by the charge of proton, which is the 1.6 negative 19 value. And I've got an electric field of a 1.02 times 10 to the negative 7 newtons per coulomb. Now, if I want to draw the field, it has to go up or down, I know that. But if I got a proton in there, I would want the electric field to be going up. So this would have to be the positive plate, and this would be the negative plate. So the electrical force is attracting it upwards. So I'd have an electric field of 1.02 to the negative 7 newtons per coulomb, having it actually go up. So now let's look at this one. Here I've got a positive charge that has a mass of 6.5 to the negative 24 kilograms, and it's balanced in 1.5 to the negative 5 newtons per coulomb. And I know it's a positively charged thing, and I'd like to know is how many excess protons does it have on it in order to actually charge a positive to let it actually be balanced the way it is. So I'm going to do the same type thing I did before in this question up here. QE equals mg. So QE equals mg again for this one, except this time I'd be looking for my Q value. So my Q value would just be the force of gravity divided by the electric field. I've got the mass, I've got the acceleration due to gravity, and I can then calculate it out. So I've got the mass, 6.5 negative 24 times 9.81 divided by E value, and I get a charge of about 4.25 times 10 to the negative 18 coulombs. So that's the charge of this guy right here. Now, if I want to know how many protons that would be, I'm just going to divide that by the E value, the 1.6 negative 19 that Millikan found. So if I divide this charge by that E value, I get 26.6 protons. But we have a problem here. You can't have a partial proton. That doesn't work. I can't have 26.6. It could be 26, it could be 27, but it can't be anything in between. It has to be an integer of the 1.6 negative 19 coulombs. Which means this setup, whatever this is not actually possible. This is an impossible setup. Your charge has to be an integer number of the E value, not electron, but E value. Okay, you'll often see Q is equal to NE, where N stands for an integer number times the 1.6 to the negative 19. This does not work. If I'd gotten like 26, fine. If I'd gotten 27, fine. If I got 26.01, I'm probably fine. It's probably just like a rounding error type thing, no big deal. But this is like 26.5. That is not going to cut it. So this setup is not actually physically possible. Okay, so that's just a little thing that can be used actually to identify elements and how many charges they might have and stuff like that. And it's just a modification and the application of the Millikan apparatus and the electric fields you guys have been working on.